Okay, so the first thing that I like to start out with on kidney here is to look at it from the macroscopic perspective, just to relate this like macroscopic kidney picture with what you're looking at in the nephron. And by the nephron, I think you know what I mean. You know, like the thing that's like the tubule where you've got all the different parts of it that go around and do this. And we'll cover that. That'll be the majority of the discussion. But I like to make the correlation between where each part of the nephron is on the macroscopic kidney. So do you have sort of a sense for that at all?
Yes, kind of.
Okay. So where is everything? I guess. That's a terrible way to ask that. Maybe if I draw this. So this is, what's this thing called where it's got like blood vessels coming into it and coming out of it?
The portal system.
Portals. It is a portal system. I haven't heard it referred to as that I know of. They may have referred to it like that in the
book, referred to it as that in the book, yeah.
Oh, did they? Nice. Okay. Yeah. Well, I haven't seen that.
At least as a whole.
Nice. Okay. So yeah, and it is a portal system. That's kind of interesting. I hadn't thought of it that way. But specifically, what are these vessels called? Like this one and this one. If we can assume one of them's bringing blood in and one of them's taking blood away, like say blood's coming into this big ball of cells right here, and then it's circulating around in here, and then it leaves via that thing.
Is that the Bowmans thing?
Yeah, exactly. So
Bowmans thing. Yep.
Bowmans, yeah. So the Bowmans thing is the Bowmans capsule is actually the tubule part of this, and so this is kind of an important distinguishment to make. I'm not going to make this one my overall nephron. I drew it too shittily to begin with. I don't want to keep going on this, but I like to draw this kind of like this to like distinguish between what is inside the tubule and what is not inside the tubule, and you'll see what I mean here in a second. It's really important to make sure you keep track of what you're referring to whenever you're talking about reabsorption and secretion and all of this stuff in the kidney, just because you can get turned around very, very, very easily. And so this first part is that you just called Bowman's capsule, is the tubule part of this very first interface between the blood and the kidney. Do you know what the blood part of it is called?
I am forgetting.
Okay, so the blood part of this, just this like ball of cells right here, like everything that's inside Bowman's capsule, pretty much, is just called the glomerulus. So, yeah, so it's like Bowman's capsule just envelops the glomerulus. So what is important about this? Glomerulus, Bowman's capsule, like what goes on there? You know, obviously it's the first interface between blood and tubule, but
the first, is this where the oh my god, okay, we're gonna make my brain work today. So blood travels through here and is first filtered.
Yeah, exactly. It's like that first spot of filtration, and that's I'm glad you used the word filtration too. So there are some really specific definitions of how to refer to stuff moving one way or the other way across the kidney or across the nephron. And so the word filtration basically just means to go from blood into tubule. And the reason I drew tubule as yellow is because it's continuous with the urinary system. And so if something is going into the tubule, that means that we're getting rid of it, right? Okay, so yeah, so filtration means going from blood to tubule. But really specifically though, it means blood to tubule without burning any energy, right? So no like ATP consumption, also no utilization of like some other gradient. You know, sometimes, for instance, the best example I can think of is mitochondrion, you know, where you use the protons to make the ATP So basically just any passive process moving stuff down its concentration gradient from blood to tubule is filtration. What if it's an active process? Do you know what that's called?
If filtration is an active process.
Yeah. Like the active counterpart of filtration.
Is that the
Did you say
secretion?
something? I'm sorry. Yeah.
No,
nice.
I'm thinking.
Perfect.
Okay.
Yeah, you said it. Secretion. Perfect. All right. So
active transport. I'm remembering. Okay. Yeah.
And then whenever you're taking stuff back up, it's just going to be called reabsorption. And they'll typically refer to it as passive or active reabsorption, but there aren't super specific words. Whereas the filtration and secretion, you really want to keep track of because they will test that very, very, very subtly, just like that. You know, they'll refer to something that sounds like it's being filtered, but they'll actually say secretion, and they can definitely catch you off on that kind of stuff. It's really bullshit that they make those kinds of questions. But whatever. Yeah, and so just taking stuff back up into the blood. So, and that's kind of important because people somewhere along the way, everybody always gets turned around like halfway through this thing. I don't know exactly where it is. It's somewhere in this region. People always get mixed up to where they start thinking of themselves as being inside the tubule. And so they'll start thinking of reabsorption as pulling things into the tubule. And I don't understand why, but it happens to me too. So I don't get why our brains do that, but just so you're aware of it. So tubule to blood is reabsorption. So remember, you are the thing that is the blood. Like that is the person. Okay. All right. So, and the whole reason I put this macroscopic picture here is to refer to how this thing tracks with the macroscopic image. And so you see this artery that comes in right here? That's the renal artery. I guess they already labeled it. And so the renal artery comes in directly off of the aorta, really high pressure, high flow system. And it just branches and branches and branches like arteries do into smaller arteries and then arterials. At the level of the arterials, what happens? So
at the level of the arterials, besides blood continuously passing through, I'm not entirely sure.
Okay, so right it is.
Sorry, continue. I was just seeing if I remembered.
All right, yeah. So it is. So at the level of the arterials, this is one of the only systems where you fall from like a pretty decent sized arterial directly to a capillary bed immediately. And so what happens here is you've got I can't remember afferent or efferent. I never remember this. It's so annoying. Afferent or efferent arterial, one of them is coming in. I'm going to look it up. One of them is coming in and brings blood into the Bowmans capsule. So you've got afferent versus efferent arterial. I swear I've done this 100,000 times.
Efferent is out. Afferent is in.
Interesting. Yeah. So I used to be able to remember it using that thought process, but for some reason in recent years, I've gotten myself really mixed up thinking, is it E for exit or A for away? And they both seem like they go away. And so, yeah, sorry. That's like the worst thing I could do. But yeah, that might preclude you from doing it on the test. So I'm gonna come up with a better way to do it. But that's the way that I always confuse myself. Great tip. At least you're aware of the pitfall.
I mean, mine was always E for entrance, but
nice.
That's also
I
wrong.
Like it. Oh, is it wrong? Okay.
I think so. Isn't it?
So
isn't it efferent? Now I'm gonna be confused.
Shit.
Efferent is out. Afferent is in.
So the one with the A comes in, right? according to Google,
Pretty sure.
afferent is, yeah, it brings blood to the glomerulus. Okay. Here, I have an easy way to remember it forever. It's just A is before E in the alphabet.
Oh, stunning.
There, it's
Yeah,
fixed.
that makes sense.
Afferent.
The only reason why I remember that is just because of the efferent muscle fibers, muscle tracks.
Yeah. And efferent. I'm going to write A before E. This is for both of us. There. All right. Anyway, so yeah, so you've got the afferent arterial bringing blood into the glomerulus. And so whenever you drop immediately from a relatively large caliber vessel to tiny capillaries, you have a big change in pressure because the overall, like the cumulative surface area of capillaries tends to be way greater than the cumulative area of, or surface area of arterioles. Reason for that is simply because there's so many of them, even though they're really, really small. Each individual one is way smaller, obviously, but there's just so many capillaries. And it has to do with just how many branches that occur in between. However, here you go like straight from a relatively large caliber arterial to a capillary bed. And so all of the pressure that drops off has to basically happen immediately. And so that's really good for being able to, what would you say? It's really good for promoting filtration because you've got that pressure pushing against, pushing the fluid, pushing all the stuff into the tubule. However, it comes back to bite us later in life whenever we start to get older. Kidneys are one of the most sensitive organs to hypertension, like chronic hypertension. So you tend to get a lot of kidney damage with hypertension. It's one of the first signs that somebody's starting to accumulate a lot of hypertensive damage is just like their glomerular filtration rate, GFR, starts to drop a lot. But that's not important for this test. It's just FYI.
Just worldview.
Yeah. And I find some of this stuff is easier to remember if you get a little bit of clinical correlation every now and then. You'll get sick of it soon though. Not on this test. I mean, like later, like 2 years. Okay, so then the efferent arterial takes whatever stuff doesn't go into the tubule and just ushers it away, basically. But we're still in technically like the artery circulatory system because all the blood's still oxygenated because it really hasn't gone to do anything yet. Just a bunch of it got filtered off. And so then this is probably the most important point about the efferent arterial. Whenever the efferent arterial leaves, it doesn't just go away. It doesn't leave the kidney or anything. It literally just branches a whole bunch and follows the kidney tubule the whole way along itself. And like it sends these like really thin, high surface area vessels down following the loop of Henle. These are called vasorecta. It's kind of low yield, but really high surface area for lots of reabsorption, and continues following, like wraps around the convoluted tubule and then down with the collecting duct, and then eventually will leave. But so just so you know that it follows that tubule along the way, because we need something to take up everything that gets reabsorbed. Otherwise, the kidneys would just turn into water balloons.
Oh, wait. So just to clarify, the vasorecta is the capillaries that are surrounding and like following this.
Yeah, they're like I don't know. I don't know if I'd classify them as capillaries or arterioles
efferent
or
arterioles.
Yeah. That's basically like branches off the efferent arterioles.
Okay, cool.
Yeah.
I thought it was part of the same like loop of or like it was like some form of extension of the loop.
Okay.
Okay, cool. Good.
Yeah, it's basically just the blood that follows the loop down. Okay, so that's what the blood's up to. And so this artery that comes in, this renal artery, turns into first the afferent arterial, and then it goes into the glomerulus, and then the efferent arterial, and then follows the tubule along. And so notice how I'm trying to find a good way to draw on this. Notice how this thing, when this thing comes in, that's not a good way, that it is coming in from the very center of the kidney in what's called the renal pelvis. So like this area here is the renal pelvis. And so it's coming in through the renal pelvis, and it's also leaving through the renal pelvis whenever blood leaves the renal vein. And so in the meantime, where do you think the actually that's a bad question. So it as it passes through the renal pelvis and then heads like through the heart of the kidney, and then it continues going all the way out toward like the very outside of the kidney toward the cortex before it ever turns into actually like the afferent arterial. And so the cortex of the kidney exists where the cortex of the kidney exists, like right here underneath the capsule, underneath the outer capsule, is where this first interaction occurs. So this would be like the glomerulus here, or like the Bowmans capsule sits right there. And then so then you have like the proximal convoluted tubule, and that's just like right here along. Can you even see this? I don't know if I'm able to draw it well or not, but so it's like going along right there. And then the what's it called? The loop of Henle dives down really, really deep, all the way like into the kidney's medulla again. And then it comes all the way back up. And then you've got like the distal convoluted tubule and then the collecting duct. And so the collecting duct is continuous with the urinary system, right? So like the ureter, all of that stuff. And so each individual nephron, and nephrons really are microscopic, but each individual one spans the entire distance from like outer cortex of the kidney all the way into like inner medulla of the kidney, and then back again, and then back down again. And so so why do you think it would do that? Like, what's the advantage of traveling such a great distance? Because there's a ton of redundancy there.
Surface area.
Yeah, exactly. And that's, I just really wanted to emphasize that because surface area is one of the big, really important $1 million concepts on this test. Surface area is a big deal. Not explicitly, like I don't know how many questions that will actually ever be an answer to per se, but just being aware of that. And like, because anytime you do something really, really stupid, like travel back and forth and over the same space a whole bunch of times, there's got to be a reason for it, because biology is not going to design something that inefficient on purpose or without a payoff. Yeah. Okay. So I just wanted to show you like how the macroscopic and microscopic kidneys line up with one another, because I think that kind of helps you see where everything's coming from and going to as well, because and the fact that it's continuous with the ureter. So all the stuff in the kidney ultimately like collapses down, and so you get these things. These are called renal calyces. I don't know why they're called that, but it's just like pyramids inside the kidney. And the reason that the primary functional units of it would be pyramids is because, well, the cortex is really big and every bit of cortex has to correspond to some medulla. And so they all just kind of converge in the center. Does that, you see what I'm saying?
Yes. And you said,
okay.
Sorry, can you track back for a second to the pyramids? You said it's the shape of them, not what they're called.
Yeah. So the thing, they're called calyces, or each like individually, the individual one would be a renal calyx or calyx. I don't know exactly, but yeah. And so the plural of that is calyces, I think. But yeah. And I've seen them called pyramids other places as well, but that's just the other name for them. And then like the very last little anatomy lesson here, because anatomy is not that important, but it can be when you're reading some of the really convoluted biology passages that they have, just so that you know what you're looking at. Anytime you have a solid organ like a kidney or like a brain or something like that, an adrenal gland, you have two primary parts. One part will be the center of it, like the core of the organ, and then the other part is like the outer section of the organ. So what are those two distinct parts called?
cortex and the
Nice.
medulla, much like
Yeah,
the
yeah, exactly.
adrenal gland.
Yeah, yeah, yeah. So cortex and medulla are, and that's going to be the case for every, like, kidney, adrenal, brain. I think the thyroid does it too. Heart doesn't, because heart is mostly muscle. But anyway, yeah. So cortex outside, medulla inside, and okay. So that, yeah, I think that's the end of our anatomy for today. Okay, so on to the actual nephron itself. So we talked about the Bowman's capsule and all of that already. Oops. And so what is the first segment of the nephron after the Bowman's capsule referred to as?
What is the first segment after the um I know their location, but not the name of the segments.
Do what? Oh, you say you
I
know
don't
the
think I know the
location.
name of the segment. Yeah, I don't think
Okay.
I realized they had a name.
Yeah, so it's called the proximal convoluted tubule.
Oh,
So
got
like,
you. Yeah, mhm, I'm there now.
you got it. Okay.
Yeah, okay.
Yeah, so proximal convoluted tubule. What matters or what's significant about the proximal convoluted tubule? Any idea? If you
Well,
don't
that's
know,
where
that's fine.
the filtrate or what needs to be filtered first entered. Um, yeah. Also, um, reabsorption occurs, which I've
Okay.
gathered is super important for this
Yeah.
in general.
Yeah, that's like the primary job, reabsorption,
Mhm.
filtration, basically. Yeah, so in the proximal convoluted tubule is, so it's actually the Bowman's capsule where the stuff is first going to be, where the filtration's primarily going to occur. That said,
Mhm.
filtration is going to occur everywhere, sort of, because it's not like we only have this one spot where the stuff gets in and then we're just filtering it, or we're just reabsorbing it the whole time. You've constantly got this interplay of filtration and reabsorption. However, the primary filtration does occur in the Bowman's capsule, but the primary reabsorption occurs in the proximal convoluted tubule. And if you think about it,
Okay.
the PCT, proximal, means like closest to the beginning or closest to us, basically. And convoluted is just the way I drew it, and tubulus because it's the tubule. But yeah, so tons and tons of stuff gets reabsorbed in the proximal convoluted tubule. So what kinds of stuff? For instance, you're always going to have electrolytes moving around, right? So you've got like sodium and chloride and potassium and protons and ammonium and all that stuff. So forget about that stuff for a second. We'll come to it
Mhm.
in a moment. But what is the stuff that gets primarily absorbed in the proximal convoluted tubule that you don't really see get reabsorbed in other segments of the kidney?
Water.
Water's everywhere.
Water? No,
Water gets,
water is everywhere. That would be, yeah. No, you're right. Um, besides all the salt.
yeah, besides all the electrolytes. So think about it from the ground up. Like, electrolytes are going to be the smallest things that you reabsorb. What's bigger than
Right.
electrolytes? And then where's your cutoff?
Oh,
Like,
like so many things. Yeah. Okay, so yeah,
yeah,
we have here's glucose was one of
okay.
them.
Yeah, glucose is definitely reabsorbed here.
Vitamins in general. I
Okay.
already said salts, so no salts. What else was there? Um, yeah, so water, salts, vitamins, glucose.
What about, so you talked about, so there's 4 types of macromolecules, and you and I haven't talked about this at all yet, but
Mm-hmm.
do you know what the 4 types of macromolecules are?
Like carbohydrates.
That's one. Yeah.
Okay.
You already accounted for
Carbohydrates.
those with glucose. But what are the
Yes.
other?
Macros. Protein or
Yeah,
proteins.
Protein is one. Okay. So would there be like what would be the glucose of the proteins?
What would be the glucose of proteins?
So glucose is like a monomer that makes up
Right.
big carbohydrates. So what are those for proteins?
Amino acids?
Yeah. Yeah. So amino
Oh,
acids get reabsorbed here
okay.
too. Amino acids. You're not really going to have nucleic acids at all. That's another one of them.
Oh, okay.
Simply because if a nucleic acid is outside of the cell, it is not going to be reclaimed. Like cells make all of their own. What's the last one that you haven't named yet?
Why am I thinking in terms of food?
I mean, it works. That's a really good way to do it.
Like, have I covered my vegetables? Yeah, carbs, proteins. What else do I eat? Why am I'm forgetting.
What is more fun to eat than that? Candy? Like, I mean, for me it is, but
I mean, besides, didn't we not say sugar already?
also
Isn't
in
that...
candy, aside from sugar, the other shitty thing for you.
Oh, fats.
Yeah. So the lipids
Oh
or
man,
fats, either one. Yeah,
lipids.
exactly. Yeah. So
Wow.
are those going to be reabsorbed here?
No, not here.
Why not?
They're massive.
Okay. So they're pretty
I don't
big,
remember why. I think
but
it's
they
mainly
should
just
still be able
because
to
they're
get across
not
the
water
membrane.
soluble,
Yeah, exactly. And
right?
since they're
Okay,
not water soluble, if they're not water soluble, how do they get around in the blood? Because the blood's mostly water, right?
right. Um, Transported, or there's specific enzymes that do break them down,
Okay. Well, yeah,
just
on
not
the surfaces
here.
of cells and stuff, there are enzymes that break them down, but whenever you're moving fats or anything that's hydrophobic around in the blood, you have
Mhm.
to come up with some way to get that thing to dissolve in the blood. Otherwise, you're going to just clog up your arteries and die. And remember, we talked about this some last time about the binding globulins. Like for instance, estrogen, testosterone, thyroid hormone, all of that stuff binds to proteins that are made in the liver and get shipped around in the blood that way. Remember how we talked about like TSH is the way that you would measuring TSH is the way you diagnose hyperthyroidism or hypothyroidism rather than T3 and T4 because they're all bound to proteins. And so since all the lipids are going to be bound to proteins, they can't ever get in here to begin with. And so they're not going to be reabsorbed for that reason.
Understood.
Yeah.
Okay.
Now, and so where's the cutoff? I mean, I guess I kind of gave most of that away just now by saying they're bound to proteins, proteins don't get in. So it's pretty much right here is the cutoff. You do get some like disaccharides in here and oligopeptides, meaning like small chains of amino acids will get into the tubule, but you shouldn't in a healthy person ever get protein or cells of any kind in the tubule. If you do, then there's been some severe kidney damage or more likely a poorly taken like urinalysis, basically like somebody just like didn't do a good job getting your urinalysis. But so and we do see it all the time clinically. Like you see proteins in the urine all the time that have their own specific name and everything. But just so you know, like a healthy person not going to have any proteins in the urine because they're just too big. And if a protein's too big, then a cell is going to be too big too, right? Yeah, so that's something to be aware of.
So
Okay.
are then, sorry, this is gonna go so off topic, but
Oh no, you're fine.
kidney stones, are they
Yeah,
just
good question.
massive globs of protein, or are they
Kidney
something
stones,
entirely different?
yeah, there's a couple different kinds. So calcium carbonate is the primary kind that I can remember if I remember right. This is med school stuff, but so basically like if you have too much calcium or too much carbonate in your system. It can kind of like form what's the word I'm looking for? Form precipitates inside the tubule. And so once a precipitate will start to form, then it gets easier. That's kind of like a seed for a bigger and bigger and bigger thing to grow. And then it just like gets stuck in there and it's hard to pass it through because tubule is small and stone is really big. There's also these other kinds called like struvite stones. And these are the ones where you'll see like an old man on an x-ray will have like kidney and ureter and then stone, and it'll just like completely ruin their entire. Frequently you'll have to, their kidney will be non-functional after getting one of these. Like the kidney will swell up to be like the size of like a grown person's thigh. Like it gets really, really, really big just because, if you've got this giant struvite stone, and I don't remember what struvite's made of, it's some mineral, but I mean, if you've got that, then all of the urine is just going to back up. And so the kidney's just going to swell up and get really fat. But yeah, so it's just precipitate forming in the kidney. And so that's why people say like, don't drink Mountain Dew, drink water a whole bunch, just because the more parts per million water you have, the less likely that it's to happen. Because, like calcium carbonate is a solid. And so
noted. Drink more water.
Yeah. Yeah. And so the KSP of calcium carbonate is not very high. And because of that, you need to drink water. Yeah, exactly. So just connecting all the dots. And this is the kind of stuff that you will be doing very frequently once we start going through like the UWorld stuff. Like that's what the passages are like. They're so far over your head, it's not even funny. But it does feel kind of cool because you start to see like, oh, I actually do know some stuff. I haven't been just doing nothing, just like building the world's greatest resume in college. You've actually learned something. So it's kind of cool once you start doing that. Okay, so yeah, so that's proximal convoluted tubule. You get, generally speaking, you get about 100% reabsorption of these things in the proximal convoluted tubule, just because you're never going to see glucose, amino acids, that kind of stuff in the urine of a healthy person. What's one really big exception to that? I guess not a healthy person, but where are you likely to see a whole bunch of glucose in the urine of somebody?
What comes to mind? Diabetes?
Yeah, exactly.
Oh, okay.
Yeah, and so you'll have kids. The craziest ones are the kids who have their first like presentation with diabetic ketoacidosis. And we haven't gone through any of the biochem stuff yet, but so their blood sugar will be like 700, normal is like 100. And yeah, and so but their body tissues will be in a extremely catabolic state, meaning like fasting state, even though they've got tons and tons of sugar available. Why is that?
Because they can't break it down and use it for energy.
Why can't they break it down and use it for energy? You're right.
Oh shit.
I mean, this is just like, I'm just testing.
They lack the proteins or the enzymes for it.
Okay. What actually is the case is they are unable to produce insulin. And so,
right. Oh,
yeah.
I knew that. What the heck?
Yeah. Yeah. And so juvenile diabetes is actually an autoimmune disease where the immune system, I don't know if it's humoral immunity or cell mediated. I think it's humoral immunity, whatever. The immune system starts, if we're assuming humoral, then the immune system starts to make antibodies against the beta cells in the pancreas. And so the kids' immune system just kills all of their own beta cells. And so they can't make insulin anymore. What insulin does is it binds to when like skeletal muscle, for instance, binds insulin. Do you know what it does? What the mechanism is?
When the skeletal muscle binds insulin?
Yeah. Like how does insulin make us able to break down sugar or glucose specifically? And the reason I'm hitting all this is because we just kind of skated over it in the endocrine stuff.
No, yeah. I'm gonna try to remember. I remember there was two processes. One was gluconeogenesis, and the other one was, I think, just glucogenesis. That's it.
So there's the gluconeogenesis is like the opposite. So it's the opposite of what insulin does, kind of.
Right.
So yeah.
Okay. I'm having a hard time.
Yeah, no, it's okay. So the opposite of gluconeogenesis is glycolysis.
Oh my God. Yes. Jeez. Okay.
No, you're fine. You're fine. I mean, it's been a bit since you've learned this. So yeah, so it's the opposite
It's
is
been less
glycolysis.
than a week.
What
But okay.
what what insulin does is really actually upstream of glycolysis. And insulin, I mean, I guess it does activate some of the enzymes in glycolysis, but its primary, like the primary action that we're concerned with on insulin is upstream of glycolysis. And what it does is it actually binds to since insulin's a peptide hormone, where do you think the receptors for it are?
The receptors for insulin are within the target tissue.
Okay. Where in the target tissue? Like, is it on the surface of the cells or inside the cells?
Within.
No, because it's a
No,
peptide hormone. Yeah.
Oh, you're right. It has to be on the surface. Okay.
Yeah. So it's because remember, steroid hormones are the ones that are going to be able to diffuse through the cell membrane. So their receptors will exist frequently in the cytoplasm or inside the nucleus, even versus peptide hormones are, well, peptides are proteins, water soluble in large chunks, and so they can't get through the cell membrane. So yeah, so the receptor has to be on the surface for any peptide hormone. And so whenever insulin binds to the receptor on the surface, it leads to a signal transduction cascade. Don't really care that much about what it is, but it ultimately causes these glucose channels to be inserted into the membrane. And only upon insertion of those glucose channels into the membrane can the cell actually allow glucose to diffuse down its concentration gradient into the cell. But absent insulin, the cell has no means of taking up that glucose. So even though the kid has like 7 times the blood glucose that you or I probably have ever had, that same kid's muscle tissue thinks that it's starving to death. And so it starts activating all these catabolic pathways, catabolic meaning breaking stuff down to make energy, right? Because if you don't have glucose, then you have to tear down other stuff, fatty acids, proteins to make energy. And so it goes into like this extreme catabolic state. And that's what leads to the ketosis, right? Because you start making ketone bodies, and those will acidify the blood. And so you get like extremely acidic blood and extreme dehydration at the same time. Why the dehydration?
Why the dehydration? Because
and this is bringing us back to our kidney discussion. There's a hint.
Well, if it's acidic, or are they? I don't know.
I was going to say, so it's not really directly related to the acidity, but remember we talked about glucose gets into the tubule and it gets reabsorbed in the proximal convoluted tubule, except in a minority of cases. Obviously somebody has some pathology going on if there's glucose in the urine, but one good way to make there be glucose in the urine is to just have so much glucose in the proximal convoluted tubule that it can't all get reabsorbed before it traverses the length of the proximal convoluted tubule. And so once it gets past here, we have no more channels or no more pumps for active reabsorption of glucose from tubule to blood. And so any glucose that gets past the proximal convoluted tubule, still in the tubule, will get excreted in the urine. And so glucose is water soluble, right? And so because it's water soluble, water will follow it. Water is going to go anywhere glucose goes. And so the kid that has this blood sugar of 700 or whatever is going to be producing massive urine volume at the same time because they're going to be urinating out all of this glucose, which will naturally pull water with it.
Okay.
Yeah.
Yeah.
So they'll have like crazy, crazy high urine volumes. And the word diabetes actually means that. It's a disease of diuresis. Diuresis meaning large urine volume.
Okay.
Yeah. Yeah. So that's how it kind of all fits together in that way. And I know it's kind of frustrating with me just throwing all of that at you right now, but there's a reason for it. Like the more exposure you get to it, the better, and it'll start to feel good a little later. But also FYI, this is something I learned the other day. It's kind of interesting that, that feeling of like extreme frustration you get whenever you're like studying on the 8th hour of the day and kind of hungry and just like don't want to be there doing it. Like you'll kind of get like a feeling in your stomach, like you're frustrated, sort of.
Sure.
That's actually, tell me, you may know more about this than I do. Actually, I'm remembering you're a neuropsych major. That's actually the subjective feeling, or this the subjective sign of high cholinergic tone in the brain. And acetylcholine is like the primary neurotransmitter centrally anyway that is involved with learning and memory. So if you're feeling frustrated, it's because you are learning actively.
Nice.
Yeah, thanks. That's actually true. So I mean, it's true insofar as the podcast I was listening to is true. But the guy's that's Stanford neuroscientist, so I believe him. Okay, and so you're also getting a ton of electrolyte reabsorption here too. So the proximal convoluted tubule is very much just like the center for reabsorption of lots of stuff. These are the main ones we care about. Yeah, I'm gonna leave those there. And so it's responsible for 70% of the sodium reabsorption that occurs in the kidney. Why do we care about sodium specifically? You're going to notice that trend throughout. We care a lot about sodium.
Yeah, we do. That is literally everywhere.
Yeah.
I was thinking because of dehydration, but also it is about the movement of water as well because of sodium, no?
Yeah, exactly. Perfect. Yeah, sodium is
Okay.
the primary way that we move water around in the body. I think there's only like one. I can't think of a second one. I think there's one place in physiology where you talk about moving water alone, like water without sodium. Up until like less than 10 years ago, it was thought that it was actually impossible to move water by itself until this was discovered. And we'll get to it here in a little bit, actually. But anywhere else, you have to move sodium because I guess it's just for whatever reason, very energetically expensive to move water alone. And I think it has something to do with the water being like super attracted to the amino acids that like would comprise the inside of the pore for whatever reason. So, but if you're pulling it along with sodium, then that works out. And it has to do with the size of sodium. So like if you move like 100 sodiums and 100 potassiums, the 100 sodiums are going to carry a lot more water with them than potassium, just because sodium is, for whatever reason, like of just the right size that water can solvate it. Like it can form this solid like solution shell or whatever around sodium more efficiently than it can potassium. So that's why we care a bunch about sodium. FYI.
Okay. That's also helpful in reconstructing the way I view water because I truly only ever think about it as just like existing within our bodies.
Yeah.
But yeah, no, that makes sense.
Yeah. So most of the time, whenever you're moving water around, you're moving sodium around too. So
Okay.
yeah. Okay. So finally, moving past the proximal convoluted tubule, I think you can kind of see like what I meant by, sorry, I dropped my pen. By the fact that you can hit all of the systems from the kidney. Like there's just, I mean, I could just BS this forever. I'm not BSing it, but I feel like I could probably just talk about everything in physiology just based from here. Okay, so after the proximal convoluted tubule, we get to the loop of Henle. So what's going on here in the loop of Henle? Just realized I drew that like an idiot.
Well, this is when it dives more deeply into the kidney, like physically, like outside of the cortex and into the medulla.
Yeah.
As for what happens, I believe it's just more movement of the ions, so sodium and chlorine, and movement of water as a result as well. But past that,
Okay. Yeah, there's
I didn't mark anything
one important.
significant.
I'm sorry, I didn't mean to interrupt you.
No, continue. Yeah.
I was just going to say that there's one kind of important thing to keep track of in the loop of Henle, and that is whether you're able to move water or if you're able to move salt at various different points. And so on the way down, the loop of Henle is actually permeable only to water. And so the only thing moving across this thing, across the membrane on the way down, like in the descending loop, is water. All right. And so which direction do you think water is going to be moving? Into or out of the tubule?
Out.
Why is that?
Because sodium is moving in.
Well, sodium's just
sodium is
there.
moving out. Yeah. Never mind.
Oh, you mean like on the other side? Because on the way down, sodium is not going anywhere. Only water can move on the way down.
Yeah, you're right. It's only permeable. It's not because of sodium. I'm not sure.
Do what? I'm sorry.
And if it's not because of sodium, then I'm not entirely sure. But I think
well, it ultimately is because of sodium, but sodium itself isn't moving here. It's just a pre-established sodium gradient.
Okay.
Right. So yeah, so in the way down, only water can move across the, I guess we could say, membrane. And so the water is going to be leaving on the way down. The reason is, like, obviously, like, sodium can't go anywhere. Chloride can't go anywhere. Nothing can except water. However, you've got this weird gradient that exists in the, like, I'm trying to think of what it's called. It's like extra tubular space, whatever, like the interstitial. That's what I was looking for. Interstitial space. There's this really weird gradient that exists from the cortex where you have like 200 milliosmoles per liter, meaning like 200 electrolytes per liter of water. And that's up in the cortex. And then down at the very bottom of the medulla, or at the bottom of the loop of Henle, you've got about 1,300 milliosmoles per liter. So huge difference, meaning like way more solute up here, or way more solute down here than up here. And so as we go down the loop, you get higher and higher concentration of salt outside. When I say salt, I'm meaning like any electrolytes outside of the tubule than inside. And so water will just continuously get reabsorbed all the way down.
Okay. I'm processing what you just said, so give me a second.
No, you're good.
I want to ask a question, but I don't know what it is.
Okay,
so it's simply because the bottom and where that is located, so like more within the kidney,
yeah,
is more, what was it, more osmotic? Is that osmotic?
hyperosmotic? Yeah,
Hyperosmotic. Okay, that makes sense.
Yeah, and so up here, this 270 milliosmoles per liter, that's about the same as like human blood. And so since that's where all this tubular fluid came from to begin with, it makes sense that water would kind of be like 50-50, you know, like at this point, water is maybe like part in, part out. Maybe it's at like an equilibrium. But then as you travel down, well, if this is 270 in here, and this is, I don't know, 600 here, you know, just as you go down, it gets more and more and more concentrated. So then you're just going to get more and more water moving out. Right. Okay. And so then
yeah, that makes sense.
Okay, cool. And so on the way back up, you've got two different parts of this thing. So the whole downward thing was called just the descending loop or descending limb of the loop of Henle. On the up, whatever you say, like upward journey, I don't know. You
Ascending.
get a thin ascending and a thick ascending. And so there's a little bit of a difference between the two. Do you know what the difference is?
One is diluting that I do know, or where it's thicker, it's known as the diluting segment.
Okay, I see what you're saying. Yeah.
So that's just a larger amount of reabsorption. So it's no longer just water.
Okay. Yeah. And so even in the thin part down here, you get no water moving across. Water can only move across on the way down. It can't move across on the way back up. And so in this thin part, you get only salt is able to move across the tubular membrane. And just like water had this constant gradient causing it to be reabsorbed on the way down, salt has this constant gradient causing it to be reabsorbed on the way up. Because as we go from 1300 milliosmoles back up to 270, we get less and less and less concentrated interstitial space. And so our lower and lower concentrations in interstitial space create a gradient driving salt out into the interstitial space. Like we're moving from like low concentration of sodium, low concentration of chloride to high concentration outside. But then whenever you get to the thick part of the loop, it's really the same thing happening. Only in the thicker part, the reason it's called the diluting segment is because here we're finally able to, if we want to, and we'll talk in a second about what want to means, but in the thick ascending limb, is when we're finally able to get the urine or the tubule, whatever, more or less concentrated than the surroundings. And so so how do you think you're able to do that? Because we've got only salt moving still. But now all of a sudden we're able to get the interstitial space more concentrated, or to get the tubular space less concentrated than the surroundings. And so the way that you're able to do it is via active transport. And so you're just pumping, you're using actual pumps to pump these things against their concentration gradients. And that's the reason, actually, like this is legitimately true. That's the reason that part of the limb, or that part of the ascending limb, is thicker, is because the cells themselves are actually just thicker because they've got all this machinery in the membranes. And so it just makes that part of the tubule a little bit greater in circumference. Okay.
So then that means the thin area is still just passive transport.
Yes. Yeah. So anywhere where you see me like drawing these squiggly lines on the arrows, that means active.
Yeah. But in the in the PCT, it was also active transport, right?
Yeah, that's what I did with this. Oh yeah, I guess this would be active too. Yeah, sorry. I mean, this is gonna be both passive and active.
Oh, okay.
Primarily passive, I would say. I would need to check to make sure it's active, but in my other picture I drew that I'm checking myself on, it is active. So unless I'm wrong both times, then you're right. I know that the glucose, amino acids, all that stuff, that's definitely active, because you have to get 100% of it out.
Right.
All right, so yeah, you've got this active reabsorption of sodium and chloride in the thick ascending limb. And so, yeah, so that's happening. And that turns out to be like, this is a major site for regulation of, say, like regulation of total body water. But we'll get to that in a second. First, I want to go to the next segment, then we'll have to turn around and come back, because I don't like to teach this. I do it too frequently, is I'll teach this part without teaching you the next part, and the next part you kind of need. So bear with me one second. All right. All right. So this next segment here, just like the proximal convoluted tubule, except we're further along. So what is it?
Distal.
Yeah, nice. Distal convoluted tubule. Yeah, because it's squiggly naming. And it's further away. Yeah, exactly. Okay, so what's going on in the distal convoluted tubule?
This is the most sodium reabsorption, and also not the secretion, or is it the secretion of aldosterone?
Nice. Well, it's not secretion, but this is where aldosterone acts.
Okay.
Yeah. This is like the acting place of aldosterone. Nice. Yeah. So what's aldosterone do here?
It
also one bit really quick. The vast majority of the sodium still reabsorbed in the proximal convoluted tubule. I just wanted to emphasize that really quick. Cool. So like this is just the most tightly regulated spot, but it's still like primarily absorbed in the proximal convoluted tubule. Like that's because it's 70% there. Anyway, so what were you saying? Sorry, I didn't mean to interrupt.
It promotes. Oh my god, I can't say it. Promotes the sodium reabsorption.
Okay. How does it do that?
Increasing water.
So it's not going to do that because remember, you have to move sodium to move water. So you definitely are going to increase water reabsorption here by increasing sodium reabsorption. Yeah, but the way that you reabsorb sodium in the distal convoluted tubule is you've actually got this exchange taking place that turns out to be pretty important. So there's this exchange between sodium and potassium in the distal convoluted tubule. They love this. This is high yield. And especially because it's the thing that's regulated by aldosterone. So you've got sodium being reabsorbed. But the way that we are able to do that is by secreting potassium. And so there's this exchange that takes place between sodium and potassium here. So the more sodium that you reabsorb, the more potassium you waste. But it can go the other way too. The more sodium you waste, the more potassium you reabsorb. So there's this constant interplay.
And that's why potassium is found in urine, or high urine levels of potassium. It's like one of the waste products.
Yeah, well, it's a waste product of the body. It really depends on how much you eat, how much potassium you eat, versus sodium. There's sodium and potassium have this like constant counterplay. Like if you eat a ton of sodium, then you're probably going to end up retaining some potassium. But if you don't eat at all during the day, then you're not going to get enough sodium. So you're probably going to end up wasting more potassium, but it's very, 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 very complicated. Like I can't overemphasize how complicated it is. This is the section that just screwed everybody in my med school class because it's just like extremely complicated. And we don't need to get into all of that, and I don't even remember it, even if we wanted to get into all of it. It's stupid. So what aldosterone does here is aldosterone promotes insertion of these channels into the membrane. Just like, remember I was talking about what insulin does for the glucose channels? Aldosterone does that with these sodium potassium exchangers. It like activates the sodium potassium exchangers. So more aldosterone leads to more sodium reabsorption and more potassium excretion. So you say like sodium in, potassium out.
Mm-hmm.
All right. Okay, cool. And so since we're taking sodium in and getting rid of potassium, what do you think happens to total body water then? With a bunch of aldosterone.
And water would follow the salt or the sodium.
Yeah, nice. Exactly. Perfect. Okay, cool. So yeah, water follows sodium. So what do you think tends to lead us to want to make more aldosterone or release more aldosterone?
I know this. I don't remember. I know
So
this.
it
So I
is.
know it's
Oh, go
released
ahead.
as a result of. I'm remembering. Sorry. I know it's released as a result of low blood pressure. So
Yes.
like, I'm assuming then dehydration
So
or not related.
try not to think about dehydration too much because it can get really confusing. You'll see why here in just a second.
Okay.
This is something they'll teach you in med school too. There is no such thing as dehydration per se, because it can mean a
Okay.
bunch of different things. Because it depends on if you're referring to osmolarity or uh, uh, tension. So, and
Mm-hmm.
there's two different things, but we'll get to it in a second.
Mm-hmm.
But I know what you're saying, and you're right. Like
Mm-hmm.
if you're low on water, then you're going to want to produce more aldosterone so that you can reabsorb more water, right? That
Mm-hmm.
only makes sense. Yeah. And so it's like hypotension leads to increased aldosterone. Hypertension, decreased aldosterone. All right.
Yes.
So,
Okay. Yeah.
okay, cool. All right. So then I know you also covered the cardiac stuff. I'm going to try to do this without going too deep, too much off of on a tangent because I do want to finish the kidney without like doing the entire cardiac chapter. But so whenever you're reading the cardiac stuff, what is like the primary thing that we're concerned about or what's the heart's primary job is to it's to generate pressure so that you can circulate blood through the body, right?
Yeah.
Okay. All right. So you measure how much work the heart is doing in terms of cardiac output, correct?
Correct.
Okay. Do you remember how you calculate cardiac output?
Um, how to calculate cardiac output? I
Yeah.
believe it was the heart rate and the volume.
Yeah. Yeah. Perfect. Heart rate times the
Okay.
stroke volume. Yeah, for sure.
Okay.
And so what are some of the things that you can do if you need if you need the heart to generate more pressure in order to get the same stroke volume out? Do you remember talking anything about this? The cardiac chapter is pretty
Um,
complicated too.
yeah, no, another one that had so much in it.
Yeah.
If you said if the blood volume is low.
I'm saying if pressure is really high, so blood volume would theoretically be higher here. So just think about somebody who's really overweight and has really high blood pressure and smokes 5 packs of cigarettes a day and stuff. So they are going to have higher systemic vascular resistance.
Mhm.
So in order to get the same stroke volume, their heart has to generate a much greater pressure. And so therefore it requires the heart to have a lot more power behind each pump, like watts.
So
Or
higher blood or not blood pressure, a heart rate.
so yeah, heart rate will increase some too, but I'm just saying like assume heart rate has to stay the same for now. And because they'll both go up at the same time, and the heart rate one's kind of easy to think of. So if you want to get the same stroke volume despite having greater systemic vascular resistance, you need the heart to be able to do more in every beat,
Mhm.
right? Because it's pumping against a greater resistance. And so there's a lot of different ways really two different ways to accomplish that if you're throwing out heart rate for a second. And those are by just increasing the contractility of the heart muscle. And the other way is, and this kind of also increases contractility, is by increasing preload on the heart. So increasing how much volume is in like the filled ventricle before the beat. Because as like if you fill it up completely, or if you fill it up like 95%, then that's going to stretch the heart muscle to some degree. But if you fill it up like 102%, then that last like whatever 7% I just talked about would be pushing against a greater, like it would be like winding the spring tighter, right? The spring of the heart wall, so that initial burst, you get like 100% return on that added volume that you put in from like 95 to 102% or whatever. So you theoretically get an increase in contractility just by increasing the amount of blood you start out with in every stroke. And so that turns out to be the most efficient mechanism for increasing stroke volume against a mounting systemic vascular resistance. And so that's what people do as they go, as their blood pressure creeps up, their stroke volume will just increase and increase and increase. And so what ultimately happens over time is the chamber of the heart dilates. The wall grows thinner and thinner because you're not hypertrophying the wall, you're just dilating the inside of it. So you're stretching it out. So the wall gets thinner and thinner, and the chamber gets bigger and bigger on the inside until eventually you have stretched it to its maximum capacity. And so there's no more stretching that's going to be done. And the heart is kind of just like a wet paper bag or plastic bag at that point. It's just like it can't contract all the way against that massive volume that it has, because it has relatively little power to push against the significant systemic vascular resistance. So then what happens is, and I know this is going in really far into a lot of this.
No, I'm fascinated right now. I had no idea.
Oh, okay.
Okay.
So back up like half a step really quick. How do you keep increasing preload? What do you think you have to do to keep increasing that preload in order to continue increasing every stroke volume? Like, and this is over the course of 20 years for people.
Increase preload? I mean, besides just contracting more often? Or I guess.
Yeah. So forget heart rate for a second. You're on a beta blocker, so you can't go faster.
Okay. I'm not entirely sure.
So in order to increase preload, you have to increase the amount of total blood that you have, right?
In the body? Like all?
Yeah. You have to increase the total blood in the body, because what happens is the vast majority of any of your body's blood volume is going to be in your like large veins in your legs at any given point in time. And so the only way to increase the like rate of return is either A, exercising, but these people aren't doing that, so me neither. But B, the other way to do it is just by increasing total volume so that you're getting greater pressure back up that column, like the column from like your feet up to your chest. And so you're getting more return per time. And so that's how you increase preload. So the way that you increase total blood volume in the body is by aldosterone, right?
Oh.
So because these people just have like, do what?
No, now we've made a full circle.
Yeah. So we make the full circle there, right? Yeah. So these people have increased blood volume secondary to hypertension, but also secondary to aldosterone increase. And so you see how it's kind of a positive feedback cycle, because the more aldosterone you have, the more your blood pressure goes up. The more your blood pressure goes up, the more you need to increase preload. The more you increase preload, the more aldosterone, and the vicious cycle continues. And that's what's responsible for congestive heart failure. And so eventually these people will get to the point where the preload can't go up anymore, but they still have this massive level of aldosterone. They're reabsorbing tons of sodium. And so what happens to all that fluid? Well, if the heart can't take on anymore pre-stroke, pre-beat, then essentially that means there's no more room for all of that fluid in systemic circulation. And so you've got like your veins and arteries and stuff are just bulging under the pressure of all of this water. And so what happens to all the water then at that point? I mean, it's not going to be a sudden thing.
I mean, what happens to all the water? It stays within the. Does it not just stay within the tubule? Or just like in
So I'm
general?
talking about like across the whole body right now. So like in your legs and your lungs and your
just insane
hands,
bloating
everything.
or swelling.
Yeah. And so anytime, so whenever you've got like, imagine this is, we'll say like this is a capillary or something. All right. And then the space outside of it, obviously like interstitial space, there's always going to be some interchange of fluid between the capillary and the interstitial space, right? And so you've got forces that want to pull it in. We could call them just like inward forces. And these are going to be like oncotic pressure, right? Like the pressure of all the solutes, all the proteins, all that stuff inside. And then you also have that same force pulling it out, right? Because you've got proteins in the interstitial space as well. So you've got oncotic pressure out here, also pulling it out. But then inside you have like, what would you call it? Like vascular pressure. I don't know. I can't remember the real name for it. It's like, I don't know. Abs gauge pressure. No, it's not that. I don't remember. Hydrostatic pressure. That's what it is. Yeah. So you've got hydrostatic pressure, vascular pressure. It's stupid. You've got hydrostatic pressure.
Gone with what you said. That makes more sense.
That's the problem. That's why I can't do that. Hydrostatic pressure, pushing it outward, right? Because it's just going to be like whatever the blood pressure is, pushing it out. And there's not really anything like that over here. And so as the difference between these two gets more and more and more significant, and whenever you don't have anywhere, imagine this is like a column of blood where the blood flow is supposed to be going this way, but we've got a big blockade up here because the heart can't take any more volume. So that's going to increase hydrostatic pressure in venous circulation significantly. And when it does that, you're going to get like tons and tons and tons of fluid leaving, right? Because we're basically, if you want to think back to some of the gen chem stuff, we're basically increasing the products, right? And so whenever we increase the products, it causes shift toward the reactants, right? That's now I'm reaching.
Connecting back.
I mean, that's actually, it actually is the same thing. Right. So you get tons of water leaving the vasculature into the surrounding tissues. And that's what's responsible for edema. And so like you'll definitely experience this in the hospital if you haven't already. If you go to a patient in congestive heart failure and just like take your finger and push it into their shin bone on their leg, if you push it like with any sort of civility whatsoever, you're not going to appreciate this. You have to shove it in there. And that's like one of the worst things about med school for me, like doing any physical exam stuff. You've got to like push hard on people. But you like, I've buried my finger like this deep into somebody's shin bone before, just like, because that's how much edema they have on their body. It's just like that much fluid, but it feels like it's just their bone to the touch because it's so tense, like it's so hard whenever you push on it that you really have to shove it in there. And then you can get like, I mean, I have really stupidly like awkwardly short fingers, but I can get like my whole finger into somebody's shin bone, which is kind of wild. And so
that's crazy.
That's how much
a lot of fluid.
extra volume. Yeah, that's how much extra volume they'll carry around. So and so they start to feel like they're drowning and stuff because a lot of that volume will back up into the lungs as well. And so you treat these patients by giving them diuretics, which are drugs that make you pee more, right? Same as like diabetes is a disease of diuresis. Diuretics are drugs that do this. And so So what are some mechanisms do you think, just from what we've been talking about, that might cause increased diuresis? Where might you strategically block some of these things or upregulate them to make somebody have to pee more?
Where would you want to strategically do that?
Yeah, like along the kidney specifically, because these all act in the kidney. All the diuretics act in the kidney.
When you've ingested something terrible for you.
Oh no, I'm saying like, so you've got somebody that's in heart failure and they've got
Okay.
all this extra volume on them and you want them to pee it off. And so you have to pick a place in this map, or a couple places. There's like 3 main ones, to block or to stimulate some of these channels to make the person get rid of some of their blood volume.
I would say in the loop.
Okay. Where at in the loop specifically?
In the loop of Henle.
Do what?
In the loop of the Henle on, oh, are you asking ascending or descending? I would say
Yeah. Which channels specifically?
I would say descending.
Descending. So you're gonna block. Oh, yeah, that's not a bad idea. So you block like right there, like block this one. Yeah, that's a really good idea. That's not one, but that's a really good idea. I mean, it's, you can't know that it's not one, so that's just bad luck. I was really hoping you were gonna guess this right here, because this is the primary, like most clinically significant one we do.
Okay.
But yeah, I don't know that you could have necessarily guessed that. And so this is
thick ascending.
Huh?
Thick ascending.
Oh yeah. So
Okay, cool.
if you block the sodium reabsorption in the thick ascending loop of Henle with the drug called Lasix, which you may have heard of, or furosemide. I don't know how much time you've spent in the hospital, but those are the same thing. If you block that channel or those pumps with Lasix, then that sodium has to stay in the tubule, right? And so they end up peeing out the sodium. And so I had a patient, this is a story I always tell whenever I teach this stuff. I had a patient lose 60 pounds in 48 hours from this.
Okay.
Yeah. Super crazy. Like that's how
Do they
much
not have
extra volume
heart
they'll carry out.
failure with losing that much weight that quickly, or is it fine just because it's just water?
They're in the hospital, and so lots of things are going on. Like lots
Okay.
of,
I mean, that's
yeah.
fair, but I feel like that's still so intense. Okay.
Yeah, but they do, if they wouldn't be able to get up and move around much at all, just because they're losing so much volume. But they were to like whatever cardiac function they do sort of lose in that, they make up for in ability to breathe again, because you'll get so much fluid back up into these people's lungs that they can't even lie down. Like the one common question that you ask clinically is whenever you have a patient that you suspect is in heart failure is how many pillows they need to they sleep with every night, because as they start to, like a person lying down flat, they're going to have whatever water they have in their thoracic cavity is going to pool like this, right? Versus whenever that same person stands up straight, all of that water will pool down at the bottom. And so I don't know how much of the respiratory stuff you remember off the top of your head, but whenever you're just breathing like normal tidal volume breathing, the primary work is being done by your upper lungs, just because air is light. And so it takes more to shove it all the way down to the base of the lungs. So they don't notice as much standing up as they do lying down. And so they will start to feel like they're drowning like an hour or so after going to bed, because they're literally like getting all of that water into their lungs, just because they went to lying down flat. And so they'll start sleeping with pillows, propped up underneath them to make the water pool down here more. And so the more pillows they have, the worse the heart failure is. That's kind of like a quick test you can do clinically, is just ask people how many pillows they're sleeping with.
Interesting. Okay.
Yeah, it's pretty shitty and sad, but anyway.
Yeah, I was gonna say that's terrifying, but okay.
Yeah. Yeah, yeah, for sure. So yeah, whenever you block Lasix though, or whenever you block sodium reabsorption right there, so that
Sorry.
would be plenty to get rid of that 60 pounds, right? Like it doesn't need any help. However, you do have to take another diuretic while doing that because of this other issue. And so I'm trying to think which one I want to ask you. So the other diuretic that you take is going to act in the distal convoluted tubule to, well, what do you think it does in the distal convoluted tubule? If it's a diuretic,
If it's a diuretic, then you don't want to reabsorb sodium.
right? Yeah, exactly. And so in the distal convoluted tubule, it comes in and it blocks this. And this is called hydrochlorothiazide. And this is like the primary, just like outpatient diuretic. Lasix is IV only. So hydrochlorothiazide is what people take most of the time. Like I think my mom takes it and has been forever. It's pretty harmless, but not a ton of side effects on that. Lasix has a ton of side effects that are really, really bad. And you almost always have to take hydrochlorothiazide with Lasix to make sure you don't die. And the death that you would have would be from cardiac failure. Like and I don't mean cardiac failure, I mean cardiac arrest. Sorry. So like you just stop, your heart just stops beating. So what about Lasix would cause your heart to just randomly stop beating altogether? It has nothing to do with volume.
Oh, nothing to it. Damn it.
Yeah. Yeah.
You no longer have that oh god, what was it called? What was it called? Oh, but you said it was no longer volume.
Yeah. Yeah. No longer volume.
Decreased pressure.
Okay. Not pressure either. Think back to like the
Damn.
electrochemistry stuff now. We're literally hitting everything right
Oh,
now.
oh my god. Electrochemistry.
Mhm.
Well, if you're stopping the reabsorption of all of these ions, then you decrease cellular communication by chance.
Okay. So in a
I
way,
think
yeah.
so.
So before we threw on the hydrochlorothiazide, so that's going to mess that up. So before we threw on the hydrochlorothiazide,
Hmm.
think about like what the problem was that was solving. All right. So and this would be a very hard one to guess. This is a really hard question, but whenever we put on Lasix, we're now blocking sodium from being reabsorbed in the thick ascending limb. And so
Hmm.
sodium heads on its way down to the more distal part of the tubule. And now you get a massive increase in sodium delivery distally. So whereas before maybe you had 100 sodium get delivered to the distal convoluted tubule, now you have like 1,000 sodium get delivered. And so if we have this reaction where we've got sodium inside, potassium outside, and that yields sodium outside, potassium inside, and we increase our reactant, which was sodium inside, what do you think is going to happen? It means we're going to shift the equilibrium and increase our products. And so we're going to ultimately, by increasing distal delivery of sodium, by blocking it in the thick ascending limb, we get more sodium
Hmm.
delivered to the distal convoluted tubule, which causes more potassium to have to be wasted because you're just going to naturally upregulate the amount of sodium reabsorbed in the distal convoluted tubule. Overall, you still excrete more sodium than you would have, but you're also excreting way more potassium than you would have because you're having to now, the distal convoluted tubule here is trying to do the job of itself and this. And
Hmm.
so you're just like dramatically increasing the amount of potassium you waste. And so the person will become hypokalemic very quickly. And
Okay.
yeah. And so then they will go into cardiac arrest because they've got too much driving force for potassium to leave the cell. And so cannot repolarize the cardiac tissue after you fire an action potential.
Okay. Yeah.
Yeah.
And you can no longer send any messages to
Right. Yeah.
continue
Yeah,
the heart
exactly.
beating. Okay. Yeah.
Yeah. Yeah. Because you've got that
That's
like action potential
upsetting.
graph. Yeah. You've got the action potential graph and you hit this thing and you come back down and you go right. And this looks kind of familiar, but but then maybe you just try to repolarize right here, but then you can't get below threshold. So you never get to fire another one. So that's what happens. Anyway, so that's why you throw on hydrochlorothiazide, not because the Lasix needs any help getting rid of the water, but because it needs help not killing you. Because if you block that channel also, then you're not going to waste the potassium. And so you just get rid of the sodium.
Okay.
Yeah.
So you always need both.
I don't know about always, but most of the time, if you put somebody on Lasix, most of the time they're already on hydrochlorothiazide, so it's not a big deal. You know, like if you're on one, you're kind of on the other. Yeah. And then there are another class, and this doesn't matter for the MCAT, just fun fact. There's another class that acts right here also called well, it's like all of these lactones, which we'll talk about that in organic chemistry, but all of these lactone things, spironolactone is the one I can think of off the top of my head, and they're just aldosterone receptor blockers, which is the same thing. It just acts a little bit differently. And then
I know those well.
So do what?
I know those well.
Nice. Yeah. So the so then the final segment of the kidney, just to finish up the kidney stuff, is the collecting duct or tubule, whatever you want to call it. People call it different stuff all the time. Collecting duct, collecting tubule, whatever. I think it's different places, different names at different points along it, but I don't care. Doesn't matter. So what's significant about this? Do you know or remember?
This is what determines what will be in the urine. Like it's like the final.
Yeah, it's like, well, yeah, it's like the final thing, whatever. Final one. What can be regulated here? What's reabsorbed or what's secreted or whatever?
Water. So we want to retain said water.
Nice. And so this is that one only place that I was talking about where you get water movement all by itself. So do you know what hormone regulates this?
Besides aldosterone?
It's not aldosterone here. It is.
Yeah, it's vasopressin or ADH.
Yeah, but the same thing. Yeah. ADH, vasopressin. I think I do see it called ADH more, but same thing. Yeah, so it just leads to water reabsorption. So what's the difference between vasopressin and aldosterone? This is something that people confuse a lot.
Ooh, what's the difference? One is a steroid hormone, one is a peptide.
Yes, that's true. I had to think about that one for a minute. Yeah, that's true. Okay, what else? Yeah, that's absolutely true. That's really good.
What is the difference? Besides them being two different, I mean, they're created in different places or like secreted from different places.
Sorry, I meant like what's the difference in their activity? Like which one? So we talked about how aldosterone is released if you get low on blood pressure or low on total body water, right? Vasopressin isn't super related to that at all. Vasopressin, so aldosterone regulates tension, like regulates blood pressure and total body water. Whereas vasopressin doesn't care so much about those. Its primary job is to regulate osmolarity.
Yes.
See, because aldosterone couldn't regulate osmolarity because it's just water following sodium around. And so it doesn't matter how much of it you have, you're always reabsorbing the water with the sodium.
Yeah. So it's not that increases water like reabsorption. It's that it um, increases its like osmotic ability
Yeah, it's
or
that
its
it
ability to like travel um, across the tube or through the tube.
I I see what you're saying. Yeah. Well, it is actively reabsorbed here, or at least I drew it that way. I don't remember the mechanism on this one exactly, but so it does increase water reabsorption here, but
Hmm.
it is water without sodium, and so it is uniquely able to dilute the blood, whereas nothing else is really able to do that.
Okay,
Because like if
understood.
you increase water reabsorption with aldosterone, you're also bringing sodium, and so that's not going to have the diluting capacity that ADH does. However, if you have a whole bunch of ADH released, you're not really going to get much of an increase in blood pressure at all.
Okay.
And the reason for that is just because ADH acts at a much smaller scale than aldosterone does.
Hmm.
So and I can pick arbitrary numbers and as a sort of an example. So think you've got like that your blood pressure is, I don't know, 100, say it's 10 points low. Maybe in order to get those 10 points back, you need 1,000 milliliters of water. And so aldosterone's up for that task because it can just move 1,000 sodiums and 1,000 waters come with it. And that's not precise. That's just an example, right?
Hmm.
But ADH isn't really going to be able to do that because maybe ADH can only move in that same amount of time 10 milliliters of water. However, those 10 milliliters of water that ADH can move will have a significant diluting effect on the total osmolarity of the blood. So maybe in a different scenario, you have your blood pressure is totally normal. And we already established that if you reabsorb 1,000 milliliters, it increases your blood pressure, what, 10 points? Just based on my arbitrary numbers I'm making up. And so maybe your blood pressure is fine, but you are a little bit hypernatremic, meaning that you've got a little too high sodium concentration in your blood. And so maybe those 10 milliliters will drop you down back into like normosmotic range,
Hmm.
normosmotic. Uh, yeah, whatever. It'll drop you down into having the right concentration of sodium in your blood, whereas it wouldn't really mess with your blood pressure much because we're just at that point we're moving the needle like a tenth of a point. Yeah, so ADH regulates uh osmolarity, whereas aldosterone regulates blood volume, and they're really not going to overlap at all on this test, at least. And so that's just something to be aware of. They both start with A, and so people get confused really easily. Both start with A, and they both reabsorb water, and they're both like on the back half of the kidney. Okay, so how is aldosterone made? Like, what's the process? Because this is another thing I like to kind of hit here, just because it's complicated.
Um, it's
And
made and secreted from the adrenal cortex.
okay, nice.
Uh,
So how is it regulated? Like we talked about blood pressure regulating it, right?
hmm. Yeah. So with
So
said like decrease in blood pressure, for example, it's what are they called? Like forming blocks, I guess, are created. Um, and then so let me see if it was decrease in blood pressure causes the release of oh God, what is it? Renin.
yeah, nice.
Okay, and then that triggers the response in the adrenal cortex to release
Yeah.
aldosterone. In a really large view, I know there's like
Well,
specific parts of that as well.
right, yeah. So it all starts out with these cells right here. That's why I was messing with this. These are called juxtaglomerular cells, meaning like juxtaposed to the glomerulus. We call them JG cells. JG cells have pressure sensing mechanisms in them. And so if they sense so if the JG cells sense that there is relatively low pressure in this area, then they will upregulate their release of the enzyme renin into the blood. And
So these
so
cells are contained within the glomerulus.
yeah, they're in either I want to say it's both, but it might be one or the other. Either way, it doesn't matter for your test. It's they're in the arterioles, like the afferent or efferent arterial. So that's why they're called
Okay.
juxtaglomerular. So like adjacent to or juxtaposed to the
Okay.
glomerulus.
Okay.
Yeah, and they have pressure sensing mechanisms, and the how much pressure they sense regulates how much renin they release into the blood. Renin is an enzyme that
Mm-hmm.
will float around in the blood until it encounters angiotensinogen. And so angiotensinogen is made by the liver and it
Mm-hmm.
doesn't do anything. But whenever it encounters renin, it gets cleaved into angiotensin 1. And so renin is just the enzyme that catalyzes this like reaction of angiotensinogen to angiotensin 1. And that just happens throughout the blood. Angiotensin 1 will then float around more in the blood until it will encounter eventually. This is one of the most bizarre mechanisms. It will eventually encounter some epithelial cells specifically that exist in the lungs. And only once it goes into lung epithelium does it run into an enzyme called angiotensin converting enzyme, ACE. You've heard the word ACE inhibitor before.
Mm-hmm.
Angiotensin converting enzyme hangs out there, and it will cleave angiotensin 1 into angiotensin 2. And so angiotensin 2 is actually the most important molecule in this cascade. Probably not so much for the test, but clinically it is. You do need to know that it's a vasoconstricting agent. And there's actually a lot of evidence these days too that it is very pro-inflammatory, and so likely is one of the best individual biomarkers for like how much longer you have to live for most people. Like, yeah, it's kind of crazy. Like there's been a whole bunch of research come out in the last probably like decade on this. It was really starting to get really popular when I was in med school, so we learned way too much about it. But like it can predict your probability of having cancer and autoimmunity, lots and lots of things. Anyway, so it floats around for a while and messes stuff up until eventually it runs into the adrenal gland. And so at the adrenal, it will stimulate aldosterone release from which layer?
The cortex.
Which layer of the
No.
cortex? It, I mean, this is low yield. It is, you do have to know it for the test, but it's low yield for the test.
God, which layer? Wait, don't tell me. I know this. It will in the outer layer.
Nice, yeah.
Which is called something I'm forgetting.
Yeah. It's the zone of something. I don't remember specifically the name of it, but they're called mineralocorticoids, but that doesn't matter. Aldosterone is sufficient. I think you do need to know the zona names, which is really, really, really
Yeah, I
super
think
stupid.
I do too. I just know them as 1, 2, and 3. So.
There's zona. I think it's zona. I don't remember. There's like zona glomerulosa, zona reticularis, and zona fasciculata. Those are their names. I don't know if that's the right order. I don't think it is. I think the first one I said is the outer one though. But I'm not sure about that at all. I would bet 0 on that. Anyway, so that's a whole bunch of stuff. Where does ADH come from?
ADH comes from the pituitary.
Nice.
Stimulated by the hypothalamus.
Nice. Perfect. Yep. Yeah, exactly. You're doing really well, by the way. Like I know that you feel like you're not getting anything right, but I promise you're getting more stuff right than most people that I work with on this stuff. Probably more than like almost everybody I've worked with on this stuff at this point.
For
Oh yeah, no
fueling
problem.
my ego.
Oh no, and that's something that I won't I mean, I'm not going to do it if it's not warranted, but I try to some degree, because on the whole, I think that people could use like a little bit of extra arrogance going into this test. I haven't had any students that I've worked with one-on-one. I definitely have that I worked with in Kaplan whenever I was teaching just the courses. But then that was so obnoxious. But I haven't had anybody that I've worked with one-on-one who could use like an ego decrease. Everybody, I feel like so, and you don't need to yet, but I try to tell people to start feeling yourself a little bit whenever you get close to the test, because the smarter you think you are, the better you're probably going to do. I think that matters for this test. So
Okay. I will figure out how to do that.
No,
That'll
I
be
know.
my next test.
I mean, it's easier said than done, obviously. But anyway, so this is a whole bunch of stuff. I'll send you. Actually, I may not send you this version of the notes for whatever reason. I feel like one's really ugly today. I have a better one. I'll just send you the better one. It's
if
almost
it
the
makes you
exact
feel
same.
better, this is the result of mine, and it's far uglier and messier.
I don't know. This one's pretty bad.
Yours
This
is
one,
at least colorful.
yeah, it's because I just sit here talking and coloring while I'm talking. But this one's one that I did like a little while ago. This one's actually like pretty good. So I'll send you this one. I think you may already have it actually, but I don't know. It's some people, it's the students that go a little bit slower that I end up with the prettier pictures with, because they like want me to type everything down and all of this stuff. So like, just because you and I are moving a little faster and talking about more stuff, the picture's not going to be quite as pretty, but luckily I save all of them.
Yeah.
So.
I tried taking really you should see some of my like neuroanatomy notes from school, because those are gorgeous, honestly. Oh, gorgeous notes. I drew out everything, really? But I spent so many painstaking hours for no reason. And then I stopped. I hated it so much. I was like, all right, I'm done. I need to take messy notes only now.
Yeah, I'm very bad about that. Like I have some very, very meticulously formatted notes that I've taken in the past that are terrible. Like, yeah, it got really bad at one point for me, especially in undergrad. Med school, I didn't have time to do that shit. in undergrad, I had some immaculate notes. I've got like, do you know what the website Course Hero is?
God, I hate it. Yeah, I do.
Yeah, I don't know how it's legal. It's probably not legal, honestly, but I am a like forever I've got like infinity credits with them for stuff, just because I one day needed a book and I didn't have any money at this point. It was like in med school, and I was just like, I just gave them like my entire repository of undergrad notes, and so it's just like thousands and thousands of pages of study guide. Do what?
That's incredible. You can get paid for that?
Oh yeah, you don't get, well, you can kind of get paid now, I think, if people like upload it. I haven't even looked on there. I should look on there. I might have a couple $100, but it's the rate that they pay you is really, really pathetic. Like,
I believe that.
It's like somebody would have to pay them $20 for my study guide in order for me to get like 10 cents or something. It's really ridiculous. I just did it because they give you like free credits for stuff on their site, and I needed a book that was on there, so I needed to pirate this book at the time. But anyway, so
pirating textbooks is the only way I got through undergrad, to be fair.
Yeah, I didn't do it as much I didn't do as much as I should have in undergrad. And I feel like and then in med school they just had a syllabus for us for everything. And by syllabus, I mean like everything you need to know for this section. So they give us like, it was about 700 to 900 pages every 3 weeks is what we would get on that.
Cool. Noted.
Yeah, not fun.
Speaking or material wise, are we done for today?
Good point. I think we
I was going to ask a different question.
Oh yeah, go for it. Yeah.
No, totally unrelated to anything reading wise. So if we're not, then I think I will ask it. But
okay, yeah, go for it.
You earlier made a comment, something about like, oh, I don't know how much like clinical experience or whatnot you have. Is that how? That's a bad question to ask, I guess. But do you think that as someone who like hasn't necessarily had the most clinical exposure, I would say most I've like, what's it called? Shadowed, oh, for a little while
Mhm.
or for like a few months. Um, but otherwise, most of my clinical exposure has come from like clinical research specifically.
Okay.
Do you think that is perhaps problematic or lacking?
I wouldn't think so at all.
Okay.
I've heard some people talk about some wild ass levels of clinical experience lately. And so that's the only reason that I'm not like adamantly saying no, it doesn't matter at all.
Mhm.
Because then so I'll do some asking around of some people, just to get a sense of there's if anything's changed because I haven't looked too much at like the med school application advising stuff in a little bit. But as far as like whenever I applied is concerned, and even whenever I was on the admissions committee at Southwest, because I was on the admissions committee as like a student member at UT Southwestern for a little bit,
Mhm.
they almost like it almost like laughing at people who would have like these vast like thousands of hours of shadowing and stuff like that because it's really like once you've done it a few times it's kind of all the same. And I
Mhm.
was definitely one of those people. I had way too many shadowing hours. I can only imagine how much fun they made of me. Uh, I think that what matters more is that you're able to speak about you're able to speak about why you want to be a doctor in a meaningful way where they can tell that there's some like experiential substance behind it and not just like idealism. And
Right.
so if you've done clinical research, meaning like did you talk to patients at all during that? Okay,
Mhm.
yeah. So I would think that that's more valuable than any amount of shadowing. I think probably the thing that's going to be of greatest value in that realm is stuff that would require you to be just way older than you are, which is like having been a nurse for 10 years or something like that. Obviously, like
Yeah.
that kind of stuff is going to win out and it probably should. But for the most part, the whole clinical experience thing, as far as I am aware, is just for them to make sure that people don't do what I did, which is like go to med school and then not go practice medicine.
Which I don't
Um,
think is a bad thing, or at least like where
yeah.
my parents or like from other countries have experienced, like they do that kind of thing early on. So like you're exposed to like the specifics that like maybe you want to get into, whereas on our
Mhm.
end or like within our system, that's like so not the case. You know,
Right. Yeah.
then that's where the blind idealism happens, you know. So yeah, I
Right.
know. I just wanted to gauge that because it's like, oh, I don't know if I ever really thought about clinical hours in general or like how much I was putting in.
Yeah, yeah. I think that
So yeah.
I mean to me it probably sounds fine. And you can if you have anybody who you've like shadowed or something who can write a letter, like then that kind of thing just almost washes makes it a wash. You know, like if you've got enough clinical experience where somebody could speak to it. But if you did a research project in it, I would say that that's probably even more valuable because most people, I would guess, who are applying to med school are don't have even an opportunity to do any clinical research at all. I didn't do any clinical research till I was like second year in med school. And I was doing all of the like all of the things. So my residency application was going to be pretty badass. But then I was like, I don't even want to be a part of this anymore. So, um, but anyway, I think that it sounds to me like you're in a pretty good spot overall. And is your I'm assuming your GPA is good and all of that stuff too, but just from
Hmm.
having worked with you on here. So if it's not, then it just means that you screwed around a whole
I
bunch your
mean,
first couple of years of college.
hey, it's not the best, but it's also not tanks.
Yeah, no, that's fine. Especially if it's like if you do have missing GPA points, if they're from the first couple of years, it's better than if they're from the last several years. But I'm sure
Oh
that's
my
stuff
God,
you
yeah.
covered. Yeah,
Ironically, it's none of my science classes. That was the fun part. I tanked my
nice,
philosophy classes. Those are
nice.
great. Yeah.
Yeah, cool. Well,
They were
yeah, I don't think
too
anybody
much
cares. I really
information, but they were
no,
fun.
oh no, it's totally fine. I am the master of TMI. Like I'll just say random shit about myself sometimes. Um, anyway, like so I've been trying to edit a bunch of these videos that we've been doing because I'm trying to figure out how to do like how to cut them up and make basically like a YouTube channel without violating, like without putting you on YouTube and putting all of the students that I have on YouTube like crazy because that's, even if I ask people, like, it's just not really the right, it's not really,
Mhm.
I can ask you and then put you in the awkward position of saying no or being all over YouTube. And so I'm trying not to do that. But and also wanting to make like these discussions into like 15-minute clips anyway. In doing that, I've been forced to watch myself do this a whole bunch. And I hate it so much. Like
Oh
I'm just
God,
like,
I'm so
I
sorry.
just want to hit my face on the table whenever I'm like watching myself go back and say awkward shit on these uh videos. It's pretty pathetic, but yeah. So I don't know if you've ever done anything
Mm.
performative or not, but I feel their pain now, like all the performance people.
Yeah, I was a theater kid for a while. I know it
Oh,
well.
were you?
It's a painful time.
Nice. Yeah.
Horrible to look back on, but I don't know. Everyone I know at least knows the Khan Academy videos on YouTube and all of that fun stuff,
Yeah.
or
Yeah.
like ASAP Science or whatever those are. I live for those first of all. But
Oh,
all of
really?
those are like, I mean, if you literally already have the screen recordings of the, I mean, obviously like your desktop and the notes that you were showing me as we were talking about it. So like unless you want to project faces or whatnot, you can literally just have that as the video.
Yeah,
That's what a
that's
lot of
fair.
people on YouTube do as well, at least. I don't know.
Yeah. 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 And I've been working with a couple different things, trying to figure out good ways of going about it, but I'm not in that much of a hurry on it. I do want to get more students right now, because I guess this is like the slowest part of the year for getting new people for MCAT, because it's like everybody who is going to try to take it in January probably already is working with someone. And then like there's not another test until March. And so I'm just trying to to navigate that. So if you know anybody, I'll send you like several $100s on Venmo if you get anybody.
Yeah, I'll ask
So
around.
anyway,
I'll ask
yeah, that'd
around.
be no, like I'll seriously send you like 5 or 10% of whatever they
Oh my
buy.
God.
And then the deal I made with Omar and all the other students I've had is it's always five. Like I think that's in the contract actually. I tell people that I'll give you 5% of whatever anybody purchases from you. But like right now, I've got a couple people working on sales for me and they're doing nothing. They've done literally nothing. So yeah, so I'd be down to give you even 10% of it if you can find people. But
Yeah.
we'll see.
See, this is my problem. I know no
Do
no
what?
MCAT people. I don't know anyone trying to take the MCAT, but I will look for
Oh,
them.
dang. All right.
I'll put out feelers into the community, see what happens.
Yeah, yeah, you'd be my hero if you got got some people. But yeah, because right now I'm the least busy that I can remember ever being, other than just building advertisements, which is really not fun. But
Yeah.
yeah, I've learned never go into sales. Sales sucks. I hate it.
Yeah.
But anyway, I will stop rambling about that stuff. Really quickly, what do you want? Do you have any preferences on stuff to do for next time? I know you did
No,
those.
I mean, so okay, so now we can cross off, what was it, 10 through 12 on
Yeah.
physics as well, which were honestly maybe my favorite readings this entire
Yeah, those.
time. It was beautiful. Um, yeah, I guess we're done with biology. That was a wild ride. I guess I have to stop avoiding orgo eventually. So biochem and orgo is probably our
Right.
next bet.
Yeah, that's like the next thing on the list. I'm going to put an asterisk by immune system so that we can come back to it
Okay.
sooner rather than
Yeah.
later, just because we didn't get to talk about it at all really today. Um, yeah, and we'll work it in one of these days whenever we have less stuff.
Mhm.
Okay, so in terms of, yeah, you still got these three in physics basically, and then all of the biochem and organic chem, which sucks. But I mean, that's just how this ends up
No, I
working
know
out.
I
I think
feel
it's better
at the
like this too.
beginning it would have sucked. Now I feel
Mhm.
more like mentally prepared or like
Yeah.
emotionally prepared for it.
Yeah, and I
So
think that
I'm
it
down to
builds,
do whichever or both, really.
they both build very heavily on like the initial physical science stuff too. So
Okay.
um
Beautiful.
let me look at it. So I've done this with a lot of people now. I'm trying to remember exactly what the best way of going through this was. So I think it's like the first four, yeah, it's the first four OChem reactions. The first four OChem chapters kind of go together independent of anything else, more or less. as do like the first 3 biochem chapters. And so obviously you don't have to do all of those. And are you wanting to meet on Friday again or Saturday, or what are you thinking there? I just want to make sure that you have time to have them spaced out too.
I would do Friday because my Saturday is going to be kind of weird this week.
Okay, that's totally fine.
Yeah, okay, I will try to finish all 7 by Friday.
Oh, well, yeah. If you want to try to do all of 7, you can. But that's what I was trying to think. If it's 48-hour turnaround, like that's pretty quick for 7 chapters. So you could also just do like, I don't know, pick some of them, and it's up to you though. The quicker we get through this first pass, the quicker we get through everything. So
True.
Totally up to you. The biochem stuff I'm looking. Okay, yeah, that would actually be reasonable. The biochems, this round of biochems, not that bad, except for maybe like the enzyme kinetics stuff. I don't know how comfortable you are with that, all of that business. But
I mean, I will review it and find out.
Okay, all right, yeah. And then those OCHEM chapters really aren't terrible. I mean, like the nomenclature thing is, I don't even know that stuff right now. Just being honest, like that's something that you almost don't need to know at all. Yeah, you almost don't need to know it at all.
At least like the basic endings and beginnings,
right?
Always,
Right.
But I feel like they're present and sprinkled throughout all of the material. Like we literally were talking about alls and
right, exactly. And you'll go through so many practice questions between now and real test that it kind of takes care of itself. Isomers, we can definitely talk about. I don't know what it means by bonding here. I mean, I know what a bond is.
Could mean anything.
Yeah. I'm trying to. I don't remember those chapters super well, honestly. I'm gonna look back over them before we do it, because
I think I will be able to finish all of them by Friday.
Okay, cool. Yeah, and I'm gonna do those. I'm definitely gonna look at a couple of those OCHEM chapters. Okay, yeah, and yeah, no rush. I'll be good to go either way. Yeah, and then we'll only have like, you're getting really close to kind of being done. It's just because like this is kind of a question mark, you know what I'm like, that is whether we spend any time on that together. I think we already talked about it once, but not super useful to go through together unless you have like specific stuff other than like the visual system and things of that nature. But up to you. We'll see where we are.
That was always a big question mark on why, first of all, why did they include that in the behavioral science book? I don't know. I feel like that should have been in like physics or something. But
yeah, or biology.
How much of that is really in depth? Like, do I need to know the senses and the processes that the sense of like smell and how we smell or how we see?
Vision is going to be the most important by far. And so we'll talk about that for sure. And then probably hearing, I would say, is next. And that's far less than vision, but you still need to get the basic idea of like transducing the, like mechanical vibration into a neural signal. That's the basic idea behind it. And then smell, I don't think that smell and taste are really covered at all. And so it's really just hearing and vision that I can think of right now. But and obviously I don't think that there's any like peripheral nervous system stuff either. I mean, in terms of like sensory nervous system, because that's something that I don't think a lot is known about it, period. Yeah, so there's not that much there. And honestly, the people so I've talked to, I think I've told you before, I have one guy who I talked to who has been doing this for 20 years as his career. And he is of the belief that you can do only the UWorld questions for PsychSoc and get a perfect score on the test in PsychSoc, having no background whatsoever. And so, yeah. And so I tend to believe him on that, just because he's not one to really like overemphasize something that's just wrong, that's going to screw people over. That said, I would still read the book and just give it due diligence. And I know you kind of majored in that stuff too. So
Yeah.
we'll see. Yeah, we'll see how much of that you want to actually cover. But in the meantime, we'll just focus on getting through these two steep sciences, because these two are, especially the biochem book. Biochem book's got so much shit in it. There's just more. This like a whole semester course in that book. It's kind of ridiculous. It's written differently than the other ones.
Oh boy. Well, I'm prepared.
Yeah, sorry.
Okay.
And then we'll work into the rest of the physics stuff somewhere, wherever it makes sense. Or just whenever you feel like you're ready for a break from memorizing biochem stuff. That might be a good time to do that.
Noted.
All right.
All
All
right.
right. Well, I will
I'll
let
see you
you.
Friday.
All right. Sounds good. Friday, same time? Or Friday at
Yeah.
5 your time,
Friday.
right?
Yeah, so 4 your time.
Yeah, yeah. I'm
Yeah.
mostly run on Eastern time these days. So all right. I will talk to you in 48 hours then, or 45 hours.
Beautiful. Okay. See you
All right.
Friday.